we didn't get to the second item on the list yesterday, but we will today, and that's the algebra. Now, at the end of the lecture yesterday, we started talking about continuity of functions. Right? So a function, if you recall, was continuous at a point if it actually reached its target. Right? Which was the same as saying, okay, you take the limit of the function, okay, that's the target. If the function actually evaluates to that limit, then it's continuous at that point. Okay, fine. So if you're going to decide whether a function is continuous, you actually have to know how to compute all the limits. And so we're going to start by talking about how, if you take some nice function, you can break it apart into things which maybe you already know what the limits are. So that'll be the algebra of limits. And then the second thing we're going to talk about are infinite limits. So hopefully we can start this, and we'll probably have to finish it tomorrow. Not yet. Okay, so let's talk about the algebra of limits. So what do I mean by the algebra of limits? Well, there's no actual mathematical notion called the algebra of limits. It's just a way of me talking about the fact that limits are going to satisfy some properties which deal with the mathematical structure of algebras, which you have no idea what that is, but I do, so it's okay. So let's call these limit properties so that we have a better understanding what I mean by algebra. So let's let f of x and g of x be functions such that the limit as x approaches some value a of f of x and the limit as x approaches a of g of x. So I have some point A, and these two functions both have limits at that point A. I'm not assuming that they reach that target. I'm not assuming they're continuous at A. I'm just assuming that the limits exist. Okay? And everything I'm saying here is going to be true whether I'm talking about two-sided limits, which is what I have, or whether I was talking about one-sided limits. Okay, but I'll just use two-sided limits to save the writing. And also, let C be some real number. Okay, I just choose some arbitrary real number. I don't care what it is. Okay, so these are our hypotheses. The first statement we want is the following. Let's say I take my function and I multiply it by this constant c. I can again ask, so for instance, you take the function x squared and the constant 3. Okay? You can ask, well, you can talk about the function 3 times x squared. Okay, that's what this is all about saying. Okay? What can I do with this constant? Well, what would you like to be able to do with it? You'd like to be able to put it in front of the limit. And it turns out that's what happens. So constants you don't have to worry about with limits. Now, mind you, this equality is working under an assumption, right? The assumption from the beginning is that this limit existed in the first place. Okay? So if this limit doesn't exist, then you don't talk about this equality. It's only when this limit exists. Okay. Second statement. Let's say I want to add or subtract f of x from g of x. And then take the limit. So for instance, x squared minus x. Or x squared plus x. Then it's going to be exactly what you want. Right? The limit of a sum is going to be the sum of the limits. Okay. And remember, when I write plus minus, and then plus minus here, I mean, if this was a plus, then here you write a plus, and if this was a minus, here you write a minus. If it was going to switch, then I would turn that upside down. So, if I needed to give a name to these properties, I would call this linearity. And linearity is going to be a theme in this course. We're going to see later that continuity is a kind of a linear notion. Right? The derivative is going to satisfy linearity. Okay? So this will be important. And third property, what I'll call multiplicativity. So let's say you have, instead of adding them, we're going to multiply them together. What would you like to have hold? If you have the limit of a product, what would you want that to equal?
Product of the limits.
Exactly, the product of the limits. Right? Is that going to hold?
Yeah.
Absolutely. Is that going to hold for derivatives? No. That's why we had the product rule for derivatives. So this is what I would call multiplicativity. So you have some limit, say, of x squared times sine of x. That's going to be the same as the limit of x squared times the limit of sine of x. Yeah? Okay. Let's see another one. How about this? Let's say I take my function and I raise it to a power. Okay, so here r is a real number. Again, what would I like to have happen? Well, I'd like to be able to pull that exponent outside the limit. Right? That is, if I take the limit of a function raised to a power, it should be the same as the limit of the function raised to a power. So you're always trying to somehow be able to evaluate the limit of f of x first and then apply any operations. Okay. Let's do an actual limit. Okay, I have a function, x. Okay. Just go. Okay, what happens as x approaches a to that function? What does it target? A. It's just whatever the x value is, that's what it spits out. Right? As x approaches a, this function gets pretty close to spitting out a. And is this function going to hit its target? Mm-hmm. Yeah, sure, of course it will. Right? When you put in a, you do get a out. So, I mean, this function, f of x equals x, that's a continuous function. Okay, that limit is a. Why is this such a big deal that I actually give it its own letter? let's look at an example. Let's look at, give me some polynomial, some good, say a third degree polynomial. You start randomly, there's no thought needed for this. 3x cubed, okay. Minus 4x. What? Squared? Squared, okay. Plus 2x. Minus 3. Okay, good. Alright, so I'm going to take the limit as x approaches 1, say. Okay, of 3x cubed minus 4x squared plus 2x minus 3. Okay, so, well, if we use property B, then we know that we can break this limit up into 4 different limits. Right? That just says anytime you have a sum, you can break the limit of that sum up into 2 different pieces. You just have to use this 3 times to break it up into 4 different pieces. Okay? And then property A says anytime you have a constant, you can pull it out in front of the limit. So let's do that. So you get 3 times the limit as x approaches 1 of x cubed minus 4 times the limit as x approaches 1 of x squared plus 2 times the limit as x approaches 1 of x minus, well, okay, I just leave it as inside, minus the limit as x approaches 1 of 3. Okay? But now property D says I don't have to worry about exponents in the limits. I can pull those out. So I can actually put some brackets here. I don't need them. Okay, so these first 3 terms are now completely determined by property E. Right? That's the beauty of this property E when coupled with all these other properties is you take any polynomial and you can immediately rewrite it in terms of limit of x, and then you can just plug in the number. In essence, this proves continuity of polynomials. So, of course, the limit as x goes to 1 is just 1. When you cube it, it's still 1. So you get 3 minus, okay, if x goes to 1 of x, it becomes 1. You square it, it's still 1 times 4. Plus, okay, limit as x goes to 1 of x, still 1 times 2. Okay, and then the only thing we haven't actually proven using these 5 properties is how to do this one.
The limit of a constant is the constant.
Why is the limit of a constant the constant?
Because it's not a function.
Well, it is a function. F of x
It's
equals 3.
horizontal, so it's going to be 3.
Yeah, okay, it's a good horizontal line, right? And what's the target at any point? It's the same target, right? It's always 3. And of course it hits its target. Right? But certainly as x goes to 1, well, that function's always at 3. The target is always 3. Right? It always wants to attack 3. Okay, so then this is just minus 4 plus 2 minus 3. Okay. Okay, so let's add, though, to our list a part F, which is the limit as x approaches a of a constant is always the constant. Okay, so this is very useful. You can take some horrible, nasty function and you can break it up using these properties. Reduce it down to something. And mind you, be very careful here. This r is a real number. So this includes, in particular, the limit, say, as x approaches a of the cube root of x. Right? cube root of x, that's the same as x to the 1/3 power. So that means you can write this limit as the cube root of the limit as x approaches a of x. Right? Because you could pull this 1/3 power out, and then that's the same thing as doing the cube root. And of course, there's nothing special about the 3. So this is, sometimes in books they write this as a separate property, but it's really just the same property. No? So this is very nice that these limits hold. Okay, so let us do some harder limits. So let's take one very similar to something you saw in the pre-final. Let's look at the limit as x approaches 2 of x squared minus 4 over x minus 2. Okay. Now, this function is not defined. This function is not defined at x equals 2. So you can't just plug in 2, right? It's not, this function is not continuous at x equals 2 because it's not even defined at x equals 2. Right? So if I say find this limit and you say, oh, well, I normally just plug things in. It can't work, right? What will you get? You'll get, if I just plug it in, I'll get 0 over 0. And I guarantee that if I put this on a test today, somebody would write equals 2 squared minus 4 over 2 minus 2 equals 0 over 0. I guarantee somebody will do that. But this is not right. You can't just plug in the numbers unless you have a justification, like, oh, it's a continuous function. Okay? So what can you do? All right, well, those of you who've taken calculus before, you know what's going on, right? You have to manipulate this function a little bit. Okay, well, how do we do that? Well, let's see. This is x squared minus 4 is the difference of squares. And so it can be factored as x minus 2 times x plus 2. Right? And now you have something where you can cancel, right? Why can you cancel, though? Is there a reason why you wouldn't be able to cancel? Okay, well, let's talk about, very quickly, something, and I believe Tom knows the answer to this. And so he can tell you if you haven't figured it out already. All right, recall our recitation. How did we finish the recitation? What did we prove?
1 equals 2.
1 equals 2, right? How did we prove 1 equals 2? We started with two variables, x and y. We assume that they're equal. We multiply both sides by y. We subtract x squared. Okay, we factor. We cancel the y minus x's. We recall that x is equal to y, so we can substitute x for y. And of course, x plus x is 2x. We divide by x, and 1 equals 2. Right? Obviously wrong. What's wrong? Tom, what did I do wrong?
2 things. 1, we're dividing by 0, and y minus x is multiplying it by 0, so it's 0 equals 0 on the third arrow line.
This line?
Yeah.
Okay, well 0 equals 0 is certainly true.
Yeah.
But what's the other thing I did that you said?
Divide by 0.
Okay, what do you, how I divided by 0 here?
Y minus x is equal to 0.
But when did I actually do it? It's when I go from line 3 to line 4, I said I canceled these. What do I really mean when I cancel these? You're dividing by y minus x. Right? And of course, boom. When, of course, y is equal to x, so this is 0. I divided by 0, and now I get to this line. Okay, so this is patently illegal. Okay, so I can't do that. So if I start canceling here, and both of these are 0, I'm going to get anything I want. I can get 1 equals 2. Right? So how do I know that these aren't equal to 0? Well, when would they be equal to 0?
2.
When x equals 2. When I take a limit, though, what do I assume about x?
Doesn't equal 2.
It's not equal to 2. It's anything but 2, right? I get it really close to 2, but I never, ever, ever let it hit 2. Okay, that's the key. So I don't let it hit 2. So when I do this canceling, right, which is really dividing, I'm not dividing by 0. Because I'm not letting x equal 2. So this is the same as the limit as x approaches 2 of x plus 2. Okay? If I wasn't writing limits down, let's say I was just writing the function itself. If I wrote x minus 2 times x plus 2 over x minus 2 equals x plus 2, and I just didn't write anything more, this would not be a correct statement. Right? It only becomes correct when I add x does not equal 2. And then this is now inequality. But when x equals 2, you cannot, I mean, this is not true, because when x equals 2, this is 4. When x equals 2, this is not defined. So you really have to be careful when you write these sort of things. But when you're writing with limits, this is already built in. Because limit already says, I am promising I am not letting x equal 2. Okay? Okay, but now it's easy. Okay, because we can use our properties and break this thing up. Okay, you use the properties on things like this for about 10 minutes, and then you do it in your head. Because, this is pretty cumbersome. Okay, so we already know property E said that if you take the limit as x goes to 2 of x, then you get 2. And property F said that if you take the limit of a constant, it's just the constant. And so you get 4. Okay? So this is a slightly harder situation. And hopefully, you will now all write it down like this, and none of you will write it down like this. Okay? This is bad. If you ever end up dividing by 0, bad. Bad. Not good. Okay. Let's do another sort of example. I just want to show you where things can go a little wrong. Let's look at the limit as x goes to 0 of sine of 1 over x. Okay. Now, when x is really, really big, what happens to 1 over x? Yeah, it gets really, really small, right? Because 1 over x, as x gets really, really big, right? That thing, right, flattens out and goes to 0. Okay? So this gets closer and closer to sine of 0. And what is sine of 0? 0. Very good. Right? Remember your unit circle. Okay, 0's here. The y value is 0. Okay, good. Sine of 0 is 0. So as you go off to infinity, this thing is going to go to 0. Okay? Now let's see what happens as you get closer to 0. So as you get closer to 0, this thing gets really, really big, right? Okay, now what happens to sine of x as x gets really, really big? Well, let's see, let's start at 0. I have sine of 0, we just said it's at 0. Okay, now I start moving, it goes up, okay, then it's going to go down. All right, I get over to 2 pi and then 0 again. It's going to go up, it's going to go down, it's going to go up. Okay, we can't go any further, but in our minds we can. Okay, what happens to sine as you go to infinity? It just oscillates, right? Does it go anywhere in particular? No, it doesn't go to anything, right? It just keeps on going up and down and up and down until you just wish Flanders was dead. Up and down, up and down. Okay. So, as x goes to 0, this thing starts going to infinity. So what happens to sine? Well, let's see. We know one thing for sure. Sine will never go above 1, and it will never go below -1. Okay? We also know that it's going to somehow tail off to 0, and it'll still tail off to 0 over here, but we don't really care about there. We really care about the 0. So what's going on? Well, what we're doing in this case is kind of weird. We're compressing the end run behavior of sine of x, which is all into a smaller and smaller space. As x is getting really, really small, this thing is getting really, really big, which means it's doing this quite a lot. But as you get closer and closer and closer, and it's going up faster and faster and faster, it's doing this very, very fast. Right? So it ends up going, and on the other side, it's kind of tailing off over here. But as you get closer to 0, it's really, really fast. Right? Because it's going up really, really, I mean, this function, 1 over x, as x goes to 0, it's going up really, really fast. Or on the negative side, it's going down really, really fast. But sine doesn't really care. Right? We just know it's... And the closer you get to 0, the faster it's going. It's going up, 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 down, 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 up, 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 down, down, up, up. Okay? So what is it approaching? Is it approaching anything? Well, when sine went to infinity, right? Sine of x, I mean. When x went to infinity, what happened to sine of x? Did it approach anything? No. Well, the same thing has to hold here. Right? As x goes to 0, 1 over x is going up to infinity or down to minus infinity, depending on which side. Right? And so this thing can't be approaching anything either. It's just got to as fast as you can possibly think. So this limit is not existent. And it's kind of fun to, these actually all should go up to 1, by the way. It's fun to kind of plug these functions into your calculator, if you have on a graphing calculator, because it makes them go nuts, you know, and they don't know what to do about it. Because the closer you get to 0, the faster it goes up and down. And as you move away from 0, it's still kind of slow, but the closer you get to 0, it just goes really, really fast. Even Mathematica just looks disgusting when it tries to plot these things. All right, so I just want to show you this is what I'd call a pathological example. It looks reasonable, right? But it just goes nuts. And there's all sorts of fun things you can do with this function. Okay, but what I want to use it for is to properly define for you infinite limits. So my goal is to get you some infinite limits in here, and then next time we'll continue the harder limit stuff. I mean, I showed you one nice example, and that'll get you through a lot of problems. Right? You just kind of factor things around, cancel, knowing that when you're canceling, you're dividing by something, which it won't take that value. But there are some other tricks involving multiplying top and bottom by a square root, and conjugates and so forth, and we'll get into those tomorrow. But today, let's just hit these infinite limits, and then we'll have everything. So I've been using it already implicitly. And I've been using it in two different ways. Okay? The first way is the following. I haven't written it yet, but we've talked about a limit as x goes to infinity. Okay, now, when I wrote this before, this was supposed to be some value in the domain of the function. Okay, so this really requires a different definition. Okay. So what do I mean by this? Well, so if I say that this is equal to some number L, then what I mean by this is, okay, now this is going to be probably the most technical sort of definition I give in this whole section. Okay, I mean that there exists, okay, recall that this means there exists. There exists some number, and we call it m, such that for all, we call this means for all x greater than m, f of x, and here's where I'm not going to be precise, I'm just going to use this word close again. F of x is close, and maybe even I'll add a word in here to make it slightly more precise, is arbitrarily close to L. Okay, what do I mean? Let's look at f of x equals 1 over x. As x gets bigger and bigger, okay, it gets closer and closer to what? To 0. Okay? How close does it get to 0? As close as you want to get it, right? That's what I mean by arbitrarily close. Okay? Does it ever, once it gets, at some point, does it ever pop up and down and then go back to 0? No, it doesn't get away from it, right? It just always keeps getting closer. And it never gets any further away. Okay? So that's what I mean by is arbitrarily close to L. Okay? It gets close and it doesn't jump away. Okay? You could imagine a function which starts going down to 0, okay, like this, and then hops up every once in a while. Hops up. So for instance, I'll give you an example of one that hops up. What if I made this a piecewise defined function? Right? And here's the way it's going to be. Whenever x is not an integer, okay, so it's not 1, 2, 3, 4, is minus 1, minus 2, minus 3, minus 4, so forth. Whenever it's not an integer, it's just 1 over x. But whenever it is an integer, it takes on the value 1. Okay, so at 1, 2, 3, okay, well here it actually goes to the right spot. This will be 1. Here it actually makes a hole at 2 and jumps up to 1. And at 3 it makes a hole and jumps up. And at 4, right, makes a hole and jumps up. Okay, very strange function. Okay. What would the limit of this function be as I go to infinity? It's going down. Right? I mean, clearly the behavior of this picture is it looks like it's going to 0, yeah? But every time you hit an integer, it jumps up to 1. Then back down, right back to where it's going. Then back up to 1. Down, 1. What should the limit be if this is my definition?
It's still infinity, right? I mean, it's still 0.
Is it still 0, or does it not exist? Or is it 1? Well, let's see. We said that I mean, the thing that made it make sense to say that the limit of the original function, right? If I got rid of this piecewise nonsense, right? The fact that this was 0 is that you can get it as close as you want, and it's always as close as you want, right? Once it gets close, it doesn't jump away, right? And that's what we want with a limit. We don't want it to jump away, because as soon as we start allowing it to jump away, then you have to start saying, well, how often is it allowed to jump away? Right? How much is it allowed to jump away by? Right? And that gets into deeper analysis. Right. So this limit of this function, this we'd say does not exist. Because we want it to get close and stay close. Okay? So f has to get close to L and stay close to L. The calculus, if you take a typical calculus class, all your functions are going to be very nice. You won't see this kind of nonsense. Right? And so most of these definitions you don't worry about them because everything does what it's supposed to. And if you want to know what mathematicians are doing at higher levels, well, part of it is saying, well, what happens if you get nastiness? What happens if your function starts looking like this? What can we say, all right, when it doesn't get close and stay close? But don't worry, we won't deal with those issues. We'll just point them out and then move on. You can go home and have nightmares about them. So, now let's break down what I said before this. All right, I said that there exists an m such that for all x greater than that m, it gets arbitrarily close. Okay? What that means is that for as long as I want, I can have the function doing all sorts of weird stuff. Right? It's only in the long run, right? At some point, it has to stop and get close, right? But in the beginning, it could do all sorts of weird stuff, right? I could say for the first, between 0 and say 2 billion, I'm going to have it just do random things. And after 2 billion, I'm going to make it turn into 1 over x. Okay? The limit is then going to be 0. That's what this part is telling you. Is that you don't care what happens early on. You only care after some point. There has to be some point where it gets close. Right? And then it has to stay close. But all right, you don't care where that point is. It just has to be somewhere. Okay? Let's try to write the same definition, but for minus infinity. And what do I mean by x goes to minus infinity of f of x equals L? Well, you just copy the definition. Okay? Use your intuition and say, okay, what should happen here? Well, okay, I copy things. If and only if there exists an m such that for all x, okay, now if I write greater than m, it's not going to match my intuition, right? Because going to minus infinity should be going that way. And I want it to be that eventually it gets close, and I want it to be this way. So I want my x to be smaller than m. Okay, so there's some point going this way, boom, there's my m. Now all my x is smaller than m. Right? Now my function's going to get closer to something. So I just turn that greater than into a less than. And now I can keep everything the same. Right? F of x is arbitrarily close to L. Okay? And again, it has to get close and it has to stay close. So we could write, for instance, that the limit as x goes to minus infinity of 1 over x is what?
0.
It's 0, right? You think 1 over x, we only drew half of it. The other side looks like this. Okay. Now it's always negative on here, but we don't care because it's targeting 0. That's what we care about. Now it never actually gets to 0, but again, we don't care. Okay? You can't ever get to minus infinity. We don't care because in limits you're never supposed to plug anything in anyway. And even if you did, you couldn't because minus infinity isn't the number. It doesn't matter. The target is still 0. Okay? And once it starts getting close, it's always close. Okay, so use your intuition to understand this. Okay? But also remember that your intuition will fail when you start getting these pathological examples. But in this class, most of our examples will be very nice, good, dog-fearing examples. Okay, now, there's another notion of infinite limit that we need to get to. And that means that instead of putting the limit, the infinity down here, it needs to show up here as the limit. Okay, so 2. What do I mean when I write the limit as x goes to a of f of x equals infinity? Okay. Now, this really requires us to say something because I'm saying that a target, which should be a number, equals infinity, and infinity is not a number. So what can I mean by this? Well, I have to mean the following. That, okay, now I'm going to write, instead of starting with there exists, I'm going to say for every m greater than 0, how should I write this? Well, let me first say it, and then we'll try to say it. If I want it to go to infinity, then for every real number, I want it eventually to get bigger than that. Right? So I need to make sure, and not only do I want it to get bigger, but I never want it to go back down. Okay. So what I want to say is that there exists, say, some, let's say some number b, such that, okay, how do I want to get this together, right? This is always the trick in math. Okay, is you want to take something in your mind that you understand what it means. Okay, I want it to go above m, and once it goes above m, I never want it to get below m again. Okay, so the closer I get to a, I just want it to keep going up. So how do I finagle this into something? Okay, well, okay, so I certainly have the for all m. Okay, and now what I really want to say is that I can get very close to a, and as I do, it never goes below m. So in the end, I need to say something like f of x is greater than m. Okay, so what can I do here? All right, and this is when x is really, really close to a. Okay, so I might say that, well, so maybe b is not a good letter because, oh boy, if I have to use an epsilon here, I'm going to be in trouble, but maybe I will. So there exists an epsilon. I'm using it. There's your first Greek letter. There exists an epsilon greater than 0 such that if, okay, now I just don't see any good way around this. If the distance between x and a is less than epsilon, then f of x is greater than m. Okay, I just jumped the shark, as they say. What does this nonsense mean? Okay, so first, if I want to talk about the distance between two numbers, I subtract one from the other. Right? So like, what's the distance on the number line between 5 and 2? 3. How do I do that? 5 minus 2 equals 3. But what if I did it the other way? What if I did 2 minus 5? You get minus 3. Well, that's not a distance. So you make it absolute value, right? That makes it a distance. Okay, so this just says the distance. So, I'm saying that the distance is less than some number. Okay, so, I choose some level. Okay, so I have some function, it's going up to infinity. I choose any level I want, say m. Okay. Okay, now what it has to be is that actually what do I want to say? Let's use a better function. Let's use 1 over x. Okay, so here's 0. I pick some level m. Okay. I want to make sure that I get above m. And once I get to m, it never goes below it. Right? So what I say is, there is some point which is close enough to 0, called epsilon, such that if x is within epsilon, then f of x is always bigger than m. Okay? So in this case, right, here is my epsilon. Okay, it's this distance. Once I'm within epsilon of 0, my function is always above m. Does that kind of make sense? Okay. Let's break it down again. Okay. To be going up to infinity, I need 2 things. 1, I eventually want it to get as high as I want. That's what you would expect from going to infinity. And 2, I don't want it to, go up here and then drop down. Right? The same way this one, we didn't want it to jump up every once in a while. If you're going to infinity, you don't want it to keep going up to infinity and every once in a while going boop, boop, boop. You want it to go up and to keep going up. Okay? So we're saying, I pick a point. I want it to be above that m. Okay? As soon as I get pretty close to a, that's what this epsilon greater than 0 means. Okay? I'm just saying, as soon as I get pretty close to a, I'm within epsilon. Okay? There's my epsilon in this one, if I choose that m. Okay? Then I'm always bigger than it. So the for all m says I go as high as I want. And the f of x is greater than m as soon as I'm within epsilon says it never goes back below m. Okay? So if I chose a different m, let's say I choose an m prime. Okay? What's my epsilon going to be? Well, I just find this point here where it finally goes above it. That would be my new epsilon. I'll call it epsilon prime. Okay? Once I get to that point, once I'm within that far of a, which in this case is 0, I'm always going to be above m prime. Okay. Now, this is why we try to avoid these definitions in this class. I mean, I can see your faces, just like. That's okay, Tom. That's good. Okay. So don't. This is a technical definition. We write it down so that we know what we mean. Use your intuition. Okay. If it's going to infinity, it just means it just keeps going up. Right? Just like 1 over x, going to infinity. Okay. Now, wow, we're way over time. As an exercise, go home and try to write down the correct definition for the limit being minus infinity. Take this definition and try to rewrite it. And the reason why I have you do this is so that 1, you'll have seen an epsilon at some point in this course. And 2, you can't understand this definition unless you try to write one yourself. And then you'll see why this is really the only way that it makes sense to write this. Okay? And things in math are like that sometimes. You have to write it down in some nonsensical way if you want to write down what you mean. Okay? And then try to write it down in English without using math. Okay? Very good. Okay, so we'll finish this up a little bit tomorrow, and then we'll get into working a whole bunch of limit problems. Recall also, next Tuesday there will be a quiz on limits. Okay? And homework 3, as I said yesterday, is on the web. Due next Friday. I'll put homework 4 on today, and I'll probably put homework 5 on either today or tomorrow. So those will be good to look at, of course, before the quiz on Tuesday.